Chemistry with Pastor Dan. We're looking at a concept of equilibrium. Now, remember I talked about before how we lost time here at the school, so I had to cut down a lot of stuff. And this is something that sometimes isn't always covered in the first year class. But when we get into acid base, next section, there's something called weak acids, and so you really need to have some background of equilibrium. And I really had to cut this down a lot. This used to be an entire section all by itself. We would do all kinds of problems, but we're just going to show you the first one and then focus on the second concept. So equilibrium is a type of reaction where a forward and reverse reaction reach a point of dynamic balance. Now that word dynamic means changeable. It doesn't always the same. Where it balances out can change based on the circumstances involved. All right, so how do we find where that balance point is? It's a value called equilibrium product constant. Now, in order to find equilibrium product, we have our reaction. Now, you'll notice this little double-headed arrow. That means equilibrium. It goes forward, and once so much product, it's going to come back, and then it's going forward, and it's going to go back, and forward, and back, and forward, and back. Eventually, reach a point where its concentrations work itself out, and that's what we call equilibrium. All right, now the way that we find that is a value called KEQ, or some books call it KC or KP. We take the products, and the little brackets means concentrations, raising them to the coefficient as exponents. So C raised to the C, D to the D, over A to the A, over B to the B. When we do that, so it's products over reactants. When we do that, this can only be used for gases and solutions. Solids don't have a concentration because they're pure. Liquids don't have a concentration because they're pure. It's only for gases and solutions that we can use equilibrium reactions. Okay, so that means that if KEQ is less than 1, then the reaction favors reactants. There's more reactants, less products. If, on the other hand, KEQ is greater than 1, that means we have more products, less reactants in terms of what we're dealing with. All right, so I'm going to show you one reaction again, sort of like the colligative properties. I just want to show it to you so you get some understanding, but then other concepts what we're going to include in the examination. So find the equilibrium product constant for the Haber reaction. If the equilibrium, the concentration of nitrogen is, and the concentration of hydrogen is, the concentration of ammonia is. Now, Haber reaction, what is that? Haber reaction is this one right here. It's N2 plus H2 in equilibrium gives me NH3. It's always referred to that because the first scientist to study equilibrium was a German scientist named Haber. So he's given a lot of credit for it. So there we go. And we need to balance it up. So nitrogen plus 3 moles of hydrogen in equilibrium gives me 2 moles of NH3. So if we're going to do our KEQ, remember that's products over reactants. So my products here are NH3. It's going to be some exponents, and nitrogen and hydrogen to their exponents. Well, the coefficient here is 2. And the coefficient there is 3, so we put them in and just take our values and put them in there. And when we do, the value is 0.0002907, or in scientific notation, 2.907 times 10 minus 4th. You notice there's no units here. The reason we don't have units is because every time you get a new equation, you get new formulas to set them up, and so they're not consistent. So KQ, we just don't have units. We just give a number, and that number is less than 1, so that means it's favoring reactants. If we look at our numbers, there's less products, more reactants. That makes sense. All right, now the one thing we're going to push into then is a concept called LeChattier principle. Now this was developed by a Frenchman, Henri Louis LeChattier. Ooh la la, vive la différence, a Frenchman, yes. And that says that at equilibrium in a closed system, so we're not allowing it to vent, it's got to come to equilibrium. Under stress, the equilibrium will shift in the direction to eliminate that stress. What does that mean? Where it's at when it reaches equilibrium. If we put a stress on it, that will change. It's either going to go to the products or it's going to move to the reactants based on the nature of that stress. Now, there are 4 different stresses that we can do. We can change temperature, we can change concentration, we can change pressure, and we can use a catalyst. Those are the 4 different stresses we can put on it. So if we're doing temperature, we have to go back and review a little bit. We have to identify if it's endothermic or exothermic. Endothermic, again, type of reaction where energy is absorbed. exothermic type of reaction, energy is released. And the way that we identify it, if energy is increased, it will shift to the other side of the reaction. If it's decreased, it will go to the side where the energy is on. The way that I try to explain it to my students is it's slowly like a bathtub. You turn the water on the bathtub, the water flows away. So the same thing, you put more energy in, whatever energy in, it's going to flow away to the side. Bathtub, you pull the plug, it's going to go to where the plug is. So if I'm decreasing on a side, it's going to fill that side in, it's going to shift back over. So let's take a look at an example here. This reaction here of copper 2 sulfate plus sodium hydroxide, it's going to be sodium sulfate plus copper 2 hydroxide. This reaction is endothermic. We know that because energy is a reactant. All right, now, if I'm going to increase the temperature, that means I'm going to put more in. Then the reaction is a reactant, so we identify what it is. That's how we know it. It's going to shift to the other side, and if it decreases, it goes to the same side, reviewing back that concept. So in this case, if I increase it, it's going to go to the products. I'm going to end up with more products, less reactant. KEQ is going to get bigger, okay, and the KE will increase. Let's look at this one. Now we're doing sodium, magnesium plus oxygen equals magnesium oxide. We're saying this reaction is exothermic because E is a reactant. If temperature decreases, it's on that reactant side. So E is a product. Let's continue to do. Oh, let's go back there. E is on the product. So therefore, if I'm going to decrease it, I'm pulling that plug there. It's going to shift towards the product. Again, the product's going to, the KQ is going to get bigger, and you're going to get more products and less reactants in that way. All right, now, second concept, we say concentration. Concentration is exactly the same as energy. Whatever side it's on, increasing goes to the other side, decreasing goes to the same side. So let's try, we're going to increase CO2. So that's over here. So if I'm increasing it, it's going to make this bigger. It's going to shift this way. So that means it's going to shift to the products. If CO is increased, this is a reactant. So if I increase it, it's going to go the opposite way. It's going to go to the reactants there. And then if I decrease Cl2, we're pulling the plug here. It's going to go to where it is at. So that's going to go to the products in that way. All right, good. Now for pressure, pressure only looks at gases. Remember we talked about gas laws in the past. Boyle's law. Boyle's law says that if pressure goes up, volume goes down. That means we want to go sign with the least moles of gas, Transversely, if pressure goes down, volume goes up, we're going to go sign with the most moles of gas. So let's look at a problem here. CO plus O2 yield an equilibrium, give me CO2, and balance it up, we get 2 and 2. So they're all gases, so we're good there. So I have 3 moles of gas, and I have 2 moles of gas. So they're not equal, that's good. So if I increasing pressure, okay, increasing pressure, we said increasing pressure, decreasing volume, least moles. Which is least, 3 or 2? Well, 2 is, so that means the equilibrium product constant is going to shift to the products. It's going to shift to the products. Hopefully that's not too bad. All right, if I decrease pressure in the same way, it's going to go to reactants. Awesome. Okay, so last one, catalyst. Now, catalyst, what is a catalyst? Catalyst is something that lowers the energy activation. It's a substance that increases the energy of activation without being absorbed. So however much I have, at the end I will have that same amount. There's 2 main ways we do that. Either a catalytic complex, a short-lived substance that holds it together, or a substrate, a substance on which the reaction can take place. Now, when it comes to energy, reactants usually at a higher energy state than products, but we still have to overcome a specific amount of energy. We call that amount of energy the energy of activation, okay, the E sub A. We have to overcome that for the reaction to start. Now, what a catalyst does, though, is it lowers that value. It drops it down, so therefore the reaction is able to achieve itself. It will take place quicker and easier and less of a problem. So whenever it's a catalyst, what happens in terms of KAQ, always, every time, all the time, 3 times on Sundays, always the same, is no shift. Now, it is a stress. It just is going to get you to equilibrium faster. It's not going to change where equilibrium's at. So KQ, catalyst, no shift. All right, so let's take a look at a situation. I want you to find the KEQ for this reaction, BaCl2 plus O2 in equilibrium BaO plus Cl2 plus energy. So I want you to increase the temperature, decrease the pressure, change the concentration by increasing oxygen, use a catalyst, and then is the reaction endothermic or exothermic? How do you know? So let's look at energy first. Energy is over here. It's on the product side. So therefore, if I'm increasing, it's going to go the opposite way. It's going to go towards the reactants. For pressure, we got to look at the reaction, make sure it's balanced. So we balance the reaction up. Now gases. That's aqueous. That's not a gas. I've got oxygen. That's a gas. That's good. Another aqueous, not a gas. So I've got oxygen and chlorine. Those are the only two I'm looking at. I have one oxygen and two chlorines. One oxygen in the reactants, two chlorines on their products. If I'm increasing pressure, I'm decreasing volume. Side of the least number, that would be the reactants. So it's going to shift to reactants. Now, concentration of oxygen, which side is oxygen on? Oxygen is a reactant. So if I'm increasing, remember it's going to turn the water on that bathtub. It's going to go the opposite way. So that means the equilibrium product constant is going to shift towards the products. Catalyst, well, if that's not a problem, it's absolutely positively no shift. All right, and then last one, is a reaction endothermic or exothermic? Well, energy is a product, so therefore it's exothermic, and the reason is that energy is a product. All right, let's try one of these for you. So take this, pause the video, see if you can work it through, and then we'll go over the answers here in a second. So pause it, try it, do it, come on. All right, here's the answers. All right, so for the first one, it's products because it's endothermic, pushing the opposite way. Pressure is decreased, temperature is decreased, volume is increased. Most moles, that's 3, so that's the product side. Oxygen is a reactant. We're pulling the plug back to the reactants, catalyst no shift, and it is endothermic because energy is a reactant. All right, hopefully that wasn't too bad. We will practice these next, and then we'll start prepping for the test. All right, take care. God bless. Be good.